4D polar coordinates. Okay? Using the Feynman trick, we've got rid of all angular directions in terms of the integrand, and it only depends on the magnitude of a Euclidean 4-vector. Okay? So therefore, we should obviously use 4-dimensional polar coordinates here, where we want to write integral v for q Euclidean of some function of q Euclidean squared is equal to the integral v q Euclidean, I don't know what to call it. Okay, this is the answer up to the angular integral. Okay, that's the answer. And so the 2 pi to the 4th that is meant by that slash is sitting there. This S3 denotes a 3-sphere, okay, 3-dimensional sphere. S2 is the usual surface of a sphere that you know and love. The usual angular integral that you have to do in regular 3-dimensional polar coordinates is the volume, is the area of a unit 2-sphere. Okay? Well, for the obvious reasons, we now have to get the volume of a unit 3-sphere. And I'm just using this notation to say the volume of the unit 2-3. Okay, so that's the angular integral that we have to do. And but then the rest just becomes a 1-dimensional integral. Suddenly things look tractable. We're going to get just an integral in 1 dimension. So that's fantastic. We just need to get this factor right. Let's do that. It's relaxing and fun. So the problem, and we need to know this formula once we start doing things like dimensional regularization and so on. We would really like to know what the answer is, not just for S3. We all know the answer for S2. We'd actually like to know what it is for Sn. Volume of a unit sphere in n-dimensional Euclidean spacetime. Okay. So here it is. The subject of this topic is, of this digression, is this. Here's the trick. Root pi is equal to the integral dx e to the minus x squared. This is a stock standard integral. Everybody's supposed to know how to derive that. If I take it to the n plus first power, I just get that. This can be written as integral dx1, integral dxn, n plus 1, e to the minus x1 squared minus xn plus 1 squared. Okay? Because all I've done is I've written out this factor n plus 1 times. The first one I've called the integral over x1, the second one over x2, etc. Okay, so this, however, is equal to the integral of over an n plus 1 dimensional vector. Sorry, n plus 1 dimensional vector integral. E to the minus, and this thing just looks like x squared. Okay? But now let me try and do this in polar coordinates. Okay. In polar coordinates, that would look like, well, just do the integral over the radial direction, because it's only dependent on the radial direction. And to the n e to the minus r squared. That's what it would be. Except again, you have to do the angular directions. And the angular directions would give you that. Okay. Now, this, you can write it as e to the r squared half r squared to the this is correct. This is r to the n plus 1. That's correct. Here, r to the... Okay, let me see. What I have in my notes is n over 2. And then I want to write e to the minus r squared. But this is wrong, right? Because this is r to the n plus 2, so.
Wait, your change of variable should give you an extra power factor of r.
It should, but then I should cancel that against this, right? So
I'm just saying you should.
this is wrong. You're just saying that this is wrong.
Yeah.
So
Are you? Is that the issue you're?
yeah, that's what I can see that it's wrong, and now I'm trying to see it. So I think.
Oh, that's what it is, and we.
No, I think this. Now I think it's correct. What I've written is correct now.
Oh.
N over 2 minus 1 will be correct.
Oh.
No.
You think this is wrong?
No. N over 2 minus half.
This is good.
That's correct.
Oh, n over 2. Well, that's whatever. I'm okay.
Yeah.
Okay, now, this is equal to whatever, integral y to the, right? This integral has a name, which is just the gamma function. It's the generalization of factorial. You see, if this index here was a polynomial, was an integer, whatever this n minus 1 over 2 was an integer, you'd all know how to do this integral, because you'd use integration by parts to keep killing powers of y here. And then you do it, and then you find it's some n factorial or whatever, this thing factorial or something. Okay? You all know that gamma functions are, in some sense, a continuous generalization of the factorial function. This is how they are, one definition, this is the definition if you want, this is just defining the gamma function, which means it's your responsibility, not mine. Okay. Fine, so we've given it that name. Now, because I made a mistake here, and in my notes I wrote this, well, actually, we can check, because we all know S2, and we know what the gamma function is. So, we know gamma for integers. So, let's just, so hold it. I might need to correct that thing in here in a second, but tentatively, this might actually be the answer to that. Unless one of you knows off the top of your head.
You need plus a half.
Well, no, but the gamma function has a weird definition. It doesn't correspond exactly with.
Exactly.
It's off by like 1.
It's off like 1, so I'm going to check. And I know that. I know gamma n plus 1 is n factorial.
Okay.
I know that.
Okay.
Yeah, so it's y to the something minus 1, it's gamma of something.
Yeah, that's
So you need,
So you should have n plus half.
yeah.
N
you
plus
need
1 over
plus
2.
a half.
You think I need n minus 1 here?
No, and you need
N plus 1.
2 plus a half, or n plus 1 over 2.
Check the case that n equals 1. The n over 2
then we
would just give
subtract
you
1 from
root
that.
pi, which would not be right.
Yes.
Because then it go e to the minus y.
Yes.
It's not
Yes,
pi.
exactly.
Okay, well, I'm gonna go with this and I'll double check in a second. And anyway, we now need to, so this is the general thing, file it away, we'll get to it later. And we need the gamma, so we want S3, N is 3, so we need the
Gamma 2.
we need gamma line, right. We're supposed to need gamma half.
I think there's a normalization thing in the gamma.
But we know how it's normalized. Yeah, so gamma n plus 1, where this is an integer, is equal to n factorial. This is how gamma is normalized. Yes. Okay, let me offline just fix this up, or one of you will fix it up, or we will forget about it. But we just need to use this trick to do the one we actually want. I'm just showing you the general trick. Here's the one we want. We need to write root pi to the n plus 1 or 4 is equal to integral the r cubed e to the minus r squared S3. Okay, this is easier because I'm not going to talk about general, I'm just going to do the input, then we'll be done. This is equal to integral dy, where y is equal to r squared, y e to the minus y. Okay? So we just need to use the fact that this is equal by integration by parts, which I will use from now on. This is, to me, integration by parts is a half integral dy. By the way, of course, these go from 0 to infinity. As dy of y. Obvious, right? Because when it was minus d dy acting on this, that wasn't changing the answer. So minus d dy acting on this, integrate by part, puts it here, this gets rid of that, and now I just have to do the integral dy of e to the minus y, which I can do, and what is that, 1? So it's a half. And so okay, done.
What's the formula supposed to be for the unit n sphere?
For the what?
For the n sphere, what is the formula supposed to be?
For n?
Yeah, like.
If I knew that, then I would just write that one down. I mean,
Oh,
hopefully I was supposed to have written
you
it
had
down.
the answer, and you
You're-
were just
if-
concerned about the derivation. 'Cause we
No, but I
almost
don't
had
trust my
derivation.
answer. I mean, I've written something down, but I don't trust that if I got that wrong, then how many other things did I get wrong?
Right.
You may well ask.
Oh, right.
Wait for
This
equal
one
to
here is
what?
right.
2?
I think it's
For the
pi
case
to
when
the
you
power
respect
n
root
by
pi,
2
you
divided by
side
gamma
you'll
n plus
you'll still
1.
get a root pi
I
from the
just
gamma.
take it to
Have
work.
1 plus a half.
Yeah, it's right.
Exercise. Here's the trick. Here's the trick. Work it out. Why do I have it? Okay, so that's that. So therefore, let's just plug that in. the way, trivial fact, this is, what's 2 to the fourth 16? So this is
Yeah,
1
that's
over 8 pi
probably
squared.
too, so.
Okay,
And you have to
factors
do
like
this
this
one.
will appear again and again to the point where when you're just estimating things, you'll say, 1 loop, 1 over 16 pi squared, to within a factor of 2. That's probably right. I'm not going to bother calculating the integral. That is often the way work is done once you know how to calculate the integral. Honestly, you almost never do.
Raman, can I make a quick comment? Everything that is written for n case is correct. So the proof is there. I mean, I just checked. I just think the formula, it's all correct. The root pi you wanted is actually on the left-hand side.
The loose powers.
The root pi that you wanted is there. So everything is fine.
Okay. It's all good. Let's just plug this in to here. So I'm just writing sigma again. So here, for your notes, here's sigma. I'm just making the substitution and then we're done. So here I'm just writing integral the q. I'll just think of that as, so this q should be thought of as q Euclidean absolute from just the radial direction. And it's q squared. And then, now, why did I put 16? Because the point I want to get is, no, this was correct. Yeah, so. And then here, it's g squared, and here this integral is dq. Sorry, that's why. So, yeah. I'm trying to put it in the nicest, easiest form for doing the integral. So I'm making the integration variable q squared. That costs me a half and makes it 8 pi squared is 16 pi squared. Same thing here. I'm making the integration variable in one shot. We're making the step down. Integral dq squared. And then the integration variable, then there's another q squared, right? Because this is really integral dq4. And then here it's q squared plus m squared minus p squared x 1 minus x. Okay, the same as that. Okay, now everybody agrees these are easy integrals to do, except this one happens to be infinity. Actually, this one also happens to be infinity, but you can see that if you had a fixed integration limit in the UV, you could do it. So these are the indefinite integrals are doable. You know how to do this, yeah?
Oh, apologies. You know if you can move the computer stand to the right a little bit?
Yes, the one right over. Wait, can't I just take this? No. This they don't want to swallow.
Disconnect the monitor from the stand.
You know what I'm going to do is keep it like that for a second and not use this part of the board after this point. So if anybody else had not got something there, tell me. Okay, do I really need to? Yeah, maybe I should get to the serious matter that none of these integrals exist. Rather than saying, here's, I think everybody knows how to do this, so I'm not going to talk about the indefinite interval you know. What do we do about the divergences? Okay. This is all happening for Q big. Okay? For Q small, for small enough Q, it's not like there's anything bad happening. There's nothing singular happening for small Q in these intervals. This is the capital N. There's nothing happening. So there's no problem in the infrared. Our problems are all in the UV in this story. But that's where the word so you'll hear the words ultraviolet divergences. Now you know why they're ultraviolet. In fact, in great detail, we did a Wick rotation keeping the integral, just to point out how shaky our ground is right now. We actually did even the integral dq0 Wick rotation under the integral d cubed q vector was illegitimate. If we didn't, if Q is fixed, if Q vector was fixed, what I showed you was perfectly well defined. I mean, that Wick rotation story, the contours on these arcs could truly be thrown away. You can go check it yourself using the standard thinking you know about. But actually, this messes that up. Actually, the fact that we're doing it under an integral sign messes it up. And that's because secretly the whole thing is diverging on us when we do this integral. And so the behavior that allows you to throw away these contours that allow you to rotate real axis to imaginary axis, totally false. You can only rotate under this kind of integral sign if this integral was actually going to converge, which it's not. So we've got terrible problems in every step of everything we did. So we have to talk about it. Okay. So the first thing is to say where can we loosen the game at all? Okay, and you can see what physically. Where is the trouble coming from? Let's go back. So we just want to diagnose where the trouble is. And so this is the momentum Q. If you want, you don't even have to think of Q0 as the problem. If there was only a Q0 integral, you could do it. It would be finite. It's the fact that you've got the extra Q vector integrals to do that's turning this into an in-net divergent integral. But anyway, we have this Q momentum going through this loop like this. And what does it mean when the Q goes to infinity? What does that correspond to? Well, it means that this line, Q is going to infinity, this line, especially if, say, just, what does this correspond to? This line is hopelessly off-shell. That's one thing for sure. Okay? This propagator looked like when these four momenta start to get really large, you've got a lot of large four momentum, which is far off shell, and similarly here. But we know that off shell momenta in position space correspond to these 2 points not being very far apart. Okay. So large Q corresponds to the interaction points getting close. So there are two ways of pointing to the bad region of integration. In momentum space, we say there's large momenta for these propagators, and they are wildly off shell, and that's contributing the bulk of this ultraviolet divergence. And in position space, the Fourier transform of this picture, in position space, that corresponds to these 2 points. As I'm integrating all the values at which these points could be, I'm worrying about the parts where the 2 points are close together. Because when you're far off shell, the propagator is only non-zero, appreciably non-zero, for very short space-time separations. So that's the problem we are facing. And so we have to ask, do we trust this picture? Something about this picture is breaking down at very short distances. Okay? So our calculation breaks down at, if you want, high momentum or energy, or if you want small distance. Now I want to actually approach this the way an effective field theorist would phrase the problem, although ultimately we'll do better than that, surprisingly. And the way I want to phrase it is, we are very tentative experimentalists. We have seen on some detector plate some photon things looking, or we call them photons, these little blotches like this, and we say, looks like a point particle to me. And so we have tried to say, well, I believe in relativity, I believe in quantum mechanics, and I'm seeing point particles. Let me put them together, and we've written down a theory that allows us to describe these point particles interacting with each other. That is the level of tentative business that we have done so far. On the other hand, if I zoom in on that point, I don't actually know it's a point. If 2 points get close together, and they're not actually points, say the proton is not actually a point particle, it's made out of quarks and gluons, then when I start saying that the interactions are these perfect pointy things that I've described here, right? When the 2 points in space-time start getting close together, when they're far apart, it doesn't matter. A marble is a point particle if you're viewing it on a galactic length scale. But when the 2 particles get close together, or these vertices, their interaction vertices get close together, then it's possible that this approximation that we are dealing with point particles is breaking down, right? It's possible. So if we are very tentative in our statement, I believe in quantum mechanics, I do not want to give it up. I believe in relativity, I do not want to give it up. There is one thing we could give up. We could give up our blind faith that we're dealing with point particles. Or, what is really equivalent from a philosophical and experimental point of view, we could give up our blind faith that the interactions are themselves point-like. You have a point-like particle, but it's got some fuzzy interaction. You might as well call it, there's no way to probe its pointiness. You might as well call it a object, right? So, we just want to give up, we want to ask whether we should really take seriously the pointiness of our particle, and the pointiness, that is, interaction at a point of these interactions. And does it matter? Is it relevant to the thing? Yes, it seems to be absolutely at the core of what is the problem that we're facing. Namely that when these vertices get close together is precisely where the problem is. If we could only sort of in the integral over x and y, we think in position space, if we could only stop them from getting close together, in momentum space that would be like stopping the momentum from going to infinity in those integrals, and we could get a finite answer. Another way to phrase it, which is much closer to the way a particle experimentalist would think, is they say, well, I don't think in terms of space and time. I think in terms of energy and momentum. And they say, I've tested your theory of Yukawa up to GeV energies, say. And now you're telling me that because of virtual physics, because of the Heisenberg uncertainty principle, you can, in the middle of the Feynman diagram, borrow energies which are vastly higher than my experimental energy budget. and you believe your theory to energies vastly higher than anything that I, the experimentalist, have tested. Well, if you believe it, if you believe this theory is just the absolute truth, you are hitting an absolute disaster. So you must be wrong. And so I would like to say, I really don't know what's happening for very high energies. And those very high energies, even though I don't have them available, they come into virtual processes. So I'm sensitive to what's happening in super high energies, even in my modest energy laboratory. But I don't trust your extrapolation to such vastly high scales. What should I do if I don't trust it? So one thing that we can do, and that I want to do as the first step, is to just say, if the ultraviolet offends thee, chop it off. Okay? So there, we want to just say, put that in, and that's called regulate. Okay, so we're seeing, so I'm just saying that the issue we're dealing with is that we have absolute ignorance. We have developed this Yukawa theory to try and fit some basic facts, maybe with some tree-level diagrams. We've tried to fit the data to 2 decimal places. And it looked pretty good. And it was all physics below a GeV. And now, when we try to calculate the higher decimal places, why are we calculating the higher decimal places? Precisely because we know the power of precision. That with precision, we have virtual sensitivity to very high energy scales. We try to do that, and then we see, well, this extrapolation, our theory, extrapolated to arbitrarily high energy scales makes no sense. Something else must kick in at high energies and stop the madness. So, but I don't know what it is. So then it seems like I can't finish this calculation. So as step one, because we really are in a terrible, terrible impasse, truly intellectually, this was a disaster, or an incredible problem. And the first step is just to regulate the problem. Okay, so we regulate our ignorance of the far UV and its effect and its virtual effects. Okay, and we cut off. We cut off the integrals with some sort of cutoff like this, and this actually has the name cutoff. Okay. Now, that's terrible, because if we have to do that, then we have to go back and redo every step of what we just did. Okay? We have to put the cutoff in, go back. Whenever we shifted integrals, like we shifted variables, q minus p goes to q, well, can we do it with that there? Then we have to shift the integration regions. And when we rotate the contours, could we rotate it with that there? We have to go check that. We better check every single place, unless we can think of some way of putting in this cutoff, which recycles all our manipulations trivially, makes it obvious that every step of what we did is now legitimate and correct. Okay? So, another brilliant technical goal. Find a cutoff where all those manipulations go just line for line correctly through. And so, remember, this thing called regularization, it is just to pause in the madness. It's not that we've solved any problem by doing this. We recognize our ignorance. We're going to cut it off. You might say, if you cut it off, I should replace it. You might say that what really should happen is this. Integral d4q should go to integral d4q lambda, where lambda is the scale up to which I do trust my theory. And then I should add whatever new contribution, if there are, say, new particles with masses at the scale lambda that come in, change my theory, save the day. If my particles turn out to be composite at the scale, at the length scale 1 over lambda, and that comes in, and then you include that, and it saves the day, there should just be some new contribution. So there's some part where I do trust these integrals, taking into account Heisenberg uncertainty principle. It's valid up to some scale, and then truly there may be some new effect. You might think we should do this. We are going to check. Right now I'm just dropping it, because I don't know what that means. Okay? Right now I don't know, and I'm dropping it. And I'm just doing this. But even this raises the issue of, okay, recalculate everything you did, and the question is, what's that cutoff? And here is the brilliant solution to this question of, can you please not make me do this lecture again? Okay, so here it is. The trick is called a Pauli. I think it's something like VR. But anyway, everybody says Pauli-Villars, so the Pauli-Villars regulator. So you just imagine that there are some new lambda mass. So lambda is some incredibly high scale, much bigger than capital M, little m, or any experimental energy. Okay? It's really the goal of doing high precision tests, is to sense what this is. But we don't know what it is. We just imagine that there's some lambda mass particles. And we ask, what is the simplest, what's the simplest way these new particles could show up? Which is maximally similar to the way that the old particles showed up, and give us finite results. We want a vision of how new physics, beyond the model that we've written down, could solve the problem of ultraviolet divergences. Just a vision. Doesn't have to be down to every detail. Well, here's the vision. So consider, for example, this term here. Okay? Integral. Oh, what the hell? Consider this second term. Integral dq squared, q squared over q squared plus m squared minus p squared x 1 minus x. This is a piece of this diagram, right? Contains this term. If there was some new particle that coupled to the scalar, here's some so this is a mass m particle. Here are some super heavy lambda scale particles. Then, in fact, the total contribution to the self-energy of the scalar would look like this, and then there'd be another contribution like so. Okay? At least if we bought the derivation of this formula, which should give you some mathematical pause, but anyway, let's just buy it for a second. I'll fix that up in a second. Before anybody leaves, the mathematics will at least fall in place, if not the physics. Okay? So, if you bought this derivation, just add another heavy guy, and there's this. It's still just as divergent as before, unless I flip this sign. Okay? If I flip this sign, notice that before I do the integral over q, I can combine the two integrands. This integrand for large q, so the integrand behaves like 1 over q squared for large q. This is Euclidean q, okay? No ambiguity. This thing, the integrand, also behaves like 1 over q squared for super large q. I mean, asymptotically large q. But if, so with the plus sign, it would just be twice as bad, because you're doing an integral dq squared over q squared. But with that minus sign, the leading thing cancels. If I have a minus sign here, then the leading thing, this 1 over q squared and this 1 over q squared cancels, and then I can do the integral. Why? Because the next term here is order 1 over q to the 4th. This is some other order 1 over q to the 4th. I hope that's obvious. Just expand this for large q squared. The leading thing is q squared over q to the 4th. Then you'll get a q squared times this over q to the 6th, etc. Okay, so if only you can cancel these bits, even if these, so this is some. These bits may not cancel, but who cares? It's finite. It's ultraviolet finite. Okay, so that's the game plan. What's the logic of this? Can I just change the coupling here so that that happens? No, the coupling is G and it's real, and this is G prime and it's real, then well, that's not going to be it. So if you want, let me just put the G squared in. It better have the same strength so that I can just cancel these two bits. But this minus sign, there's a trick. Yep.
Well, so then we get a minus sign in that because it was a fermion, so couldn't.
So if you like, this is a relative minus sign that I need.
Yeah.
This one, I'm being sloppy about, I just picked out, and I kept all the coefficients. This one was a fermion. It came with a certain sign. So there's a simple trick for saying where this sign came from, which is to say, due to the lambda particle being spin half, we want all the factors of the gamma matrices, this, that, the other. We want it all to be a perfect replica of this. So it is a spin half particle. But we want it to be a boson. If it's bosonic, then there will be a relative minus sign here. Now, this clearly violates the spin statistics connection. It is physically not sensible to do this, which is why all that you should think this is, it plays two roles in your head. Role one, it is just a way of doing this. It's just a kind, instead of putting a hard step function in the momentum integral and saying don't integrate over q large, it's just some other dumb way of cutting off large momentum. Because then if you put a minus sign, indeed, for large momentum, you start to get very small contributions. So it does accomplish that job. You might say, but it's affecting small momentum intervals. No, it's not. Because for small momentum, this thing is actually suppressed by 1 over q to the 4th. Okay? So for small momenta, this is a very... For small momenta compared to m, for small momenta, namely all these momenta, this is actually a negligible contribution. If lambda is incredibly high, this is a negligible contribution. It's only having the effect of cutting off the ultraviolet part of the integral in some sort of soft way rather than as a step function. Now, we had no reason to say it was a step function. So in that sense, the fact that it violates the spin statistics connection, well, I'm not taking this seriously. I'm just trying to use the same math to replicate it here. Okay? It's just a trick. But it does give you a kind of vision of what new physics can do. Maybe some honest new physics, subtler than this dumb trick, which is clearly unphysical. Maybe there could be a conspiracy between all the diagrams and it could give you a finite answer. If you care, in some sense, string theory, modern string theory, has exactly that aspect to it. It has a correlation between all the things that are called particles, and there's cancellation of the bad ultraviolet behavior that any one particle would have. But that doesn't matter. I'm just that's a vision. I'm not going there. But I am trying to say I have accomplished by saying that there is a new particle, okay, with wrong statistics, I have managed to do what I asked, which is to kill that particle, kill the ultraviolet divergence. By the way, once I combine, so this is convergent. So the integral converges once we combine the integrands. Okay, you can play with it yourself. You can combine the integrands, you can combine the denominators, get a fixed common denominator, and look at it, see the cancellation, and be happy that it's all fine. In fact, all our manipulations are now legitimate. I don't mean physical manipulation, I mean the mathematical legitimate. There are two types of manipulations we did. We changed integration variables, like in one term we'd say, q minus p goes to q, things like that. If you just go through your notes and look at what would happen if you had this other term just going for the ride, like this, you'll see that at every step, that's just fine. It just, the integration variables, when you shift integration variables, there's no problem. Then that Wick rotation, that's fine again, because these integrals converge now. That manipulation where you threw away, you rotate the integral, and the arcs are thrown away because they're off at infinity and dying very fast. That's totally fine, and again, you can go and just check that fact yourself. The fact that this manipulation of even doing the Wick rotation required this inequality, no problem. It's even more, unequal when capital M is replaced by capital lambda. So that's okay too. So just check for yourself, that is an exercise, you should do it, that all of these steps are working. And indeed, just one more thing before I let you go, that just one of these particles is enough, one of these fake particles is enough to make this guy converge. But actually this first term was so bad, so-called quadratically divergent. It's going to go like lambda squared, basically. That in fact, if we just rewrite this, so it contains, so let me just write like q squared. So there's another term. So there's another term that looks like that. Okay? So we can try the same trick. Hopefully it's just one trick for everybody, for every term in the calculation. But this does not work. Just look at it. Even if the 1 over q squared part of this integrand and this integrand cancel, which they do, so the integrand behaves like 1 for large q squared. This integrand behaves like 1 for large q squared. And that's not good enough, because even the 1 over q squared part would screw up. Okay? You have a log divergent integral. So this is actually still infinity. The whole thing is still infinity. Okay? Well, I did the easy case first, but basically what these folks realized, I could have a few particles. In other words, I could have, so you could just generalize this trick to lambda 1, this is mass m, lambda 1, there's something else called lambda 2, lambda 3, lambda 1, 2, and 3 are all order lambda, some big scale up in the sky. And you can choose the statistics, so this is a boson, this is a fermion, and this is a boson. Okay? Some pluses and minuses. You can choose them, and you can choose the exact, like is lambda 1 or twice lambda 2. You just play with it yourself. You can choose it so that even this thing is converted. Namely, you cancel in the integrand, when you combine integrands, you cancel the order 1 part, you cancel the order 1 over q squared part, and you're only left with an order 1 over q to the 4th part, which then converges. To cancel both the order 1 part and the order 1 over q squared part, you just need more free parameters. In this game, that's what this does. It is ultimately a pure waste of time. Conceptually, this is very useful to just recycle what you learn, but we will end up being much more efficient. A modern practitioner of quantum field theory rarely goes through all of these steps. Okay, but you should just once. You should just once go through this and see that you can choose lambda 1, lambda 2, lambda 3, and get these things to cancel all of these guys. But the principle I showed you with this term. If you include 3 guys, that's overkill for this term. It's what you need for this term. It's overkill for this term. So what? Let's overkill it. Okay. So 3 weird new particles, and we have at least got a finite all our mathematical manipulations are being correct. Okay. Let me stop for the day. Question.
I think you answered it. I was going to say, when you're putting in another lambda 2, then make the second integral divergent again.
No. What'll happen is you'll still have, so with these 3 parameters, you should check. With these three parameters, you can make sure that both integrals are converted. That's it. Okay. It's not that you're supposed to take these Pauli-Villars particles as real physics. They are hopefully a sign of what you might hope to do legitimately by adding new particles at heavy scales, and they certainly do implement just chopping off the integral without having to reanalyze every step of